Okay, active devices. Like what? Active audio filters?
What's that?
Hmm?
What's that?
Their characteristics. And we get into operational amplifiers. I like operational amp. In fact, we're going to do those first. This is a equivalent circuit of a theoretical operational amplifier. It's basically a differential DC amplifier. In most cases, it operates between a positive and negative voltage source, so it's balanced. And it can produce an alternating output. It has an extremely high input impedance. It looks like an open circuit, basically. It has very low output impedance, probably less than 50 ohms. And it has a gain of 10,000 or more, extremely high gain, which is what allows you to use it in a lot of these configurations, which we talk about. So you can do filters and amplifiers and comparators, differential amplifiers, all kinds of kind of nifty things. So what is an operational amplifier?
Differential amplifier, that's what we just talked about, right?
Mm-hmm. Alpha sound good?
Yeah.
What is the typical input impedance of an op amp? Very, very high. What's typical output impedance?
Very low.
In the theoretical world, an operational amplifier has infinite bandwidth. It's not affected by frequency. However, in the real world, that's not true. So it has what we call the gain bandwidth product, and is determined by whatever frequency or the highest frequency you can get with unity gain. So as you go up in frequency, the gain of the amplifier drops. So when it gets down to a gain of 1, whatever frequency that is the gain bandwidth product. So for any lower frequency, if you divide the frequency into the gain bandwidth product, you'll get the maximum gain that's possible for that particular device. Does that make sense? Mm-hmm. You have the same effect with the transistor. They have a gain bandwidth product also.
It's a way of calculating what frequency is going to start affecting your circuit. Right.
Yeah, because there is a half power point, you can see in that curve. Below that is basically a constant gain, regardless of the frequency. Once you get to the half power point, you're going down at, I don't know if it's 6 dB per octave or not.
Yeah, the frequency is starting to.
So how does the gain of an ideal operational amplifier vary with frequency?
It doesn't. It says
Right.
It's ideal.
Because it's ideal. What's the gain bandwidth of an operational amplifier?
So the open loop gain equals 1.
Right.
Could you clarify what you mean equals 1?
Gain of 1. In other words, the output's equal to the
Okay,
input.
so it has no effect anymore.
Right.
Okay.
0 dB.
Okay.
You also have in the real world an input offset voltage. In the theoretical op amp, with no voltage on either input, the output would be 0. In the real world, you might have some output voltage when the inputs are open, and that's called the input offset. So whatever voltage is required to bring the output to 0 is that input offset voltage. In other words, how much you have to correct to get the device centered as 0 output. What is meant by the term op-amp input offset voltage?
B.
To bring the open loop output voltage to 0.
We got any alphas? Betas? Charlies?
Charlie.
I'm gonna say C.
Bring,
It's kind of like zeroing the meter before you take.
Right.
because that's the only point that it's gonna operate correctly on the positive and negative.
Right. If you didn't do that, you just have a DC offset. And it may not be much. Okay, so we can also use them to create filters. We call them active filters when we use an op-amp to do it. I think a lot of the audio filters that you see in the modern radios are done with active filters, because they're very easy to implement. And it's just the capacitors and resistors in the circuit that determine what type of filter it is and what its characteristics are. So it's really easy to implement and calculate. Ringing is a potential problem, and really the only way to mitigate it is to restrict the gain and the Q. In other words, the higher the Q is, the higher the gain is, more likely you're going to have ringing. It's kind of like the PA system when you talk too loud and then rings, and you just crank the volume down. So what is ringing in a filter? How can unwanted ringing and audio instability be prevented? Okay, this just shows a bunch of typical configurations just for basically amplifiers using op amps. There's probably many times this for different types of filters and other configurations. These are all different kind of amplifiers. Oh, we got a Ernest.
A1C, maybe.
So it can be used as a voltage comparator, like you'd see in a analog digital converter. They'll have this kind of circuit embedded in it. One of the simplest forms is the inverting amplifier over here on the top right, where you ground the positive input and you feed the signal in to the negative through this voltage divider. So the gain is going to be the ratio of R2 to R1. So whatever you put in on the input is going to be multiplied by that ratio, and you'll see that on the output. You can also do it as a non-inverting amplifier. It's works similar, except in this case, the gain is going to be the sum of R1 plus R2 divided by R1. which is the same as 1 plus R2 over R1. You can use it as a voltage follower, kind of like a buffer. It'll still have a very high input impedance, a very low output impedance, but has a gain of 1. So that would mean it would operate all the way up to the maximum frequency of the gain bandwidth product. Use it as a summing amplifier, where you got a bunch of like analog signals, audio signals, perhaps. It's what you see in a audio mixer, with all the slide controls. Those would all be these input resistors all summed together. You can make a differential amplifier. You can make an integrator, which in essence is a very low pass filter. Or you can make a differentiator, which is taking the derivative. So you can actually do calculus. Okay, so in the typical circuit, which is the inverting amplifier, the gain is going to be the feedback resistor divided by the input resistor. There's RF over R1. So the output is going to be the voltage in times the gain of the closed loop circuit. So what magnitude of voltage gain can be expected from the circuit in figure 7.3 when R1 is 10 ohms and RF is 470 ohms? Did you do that with your calculator?
Not yet.
What absolute voltage gain can be expected from the circuit when R1 is 1800 and RF is 68 kiloohms?
Kiloohms.
Yeah.
16,000 divided by 1800, so probably see. I see.
You rethinking it?
Yeah. We moved the decimal a couple of times there.
Yeah.
Right.
68 divided by 1.8. Approximately 68 divided by 2. Or 37.778 if you use the calculator.
37,777,78.
Well, I rounded. What absolute voltage gain can be expected? R1 is 3,300, RF is 47,000.
And that's the class I was gonna go up to. I'm doing it on Zoom.
The Hobbs,
It's at Hobbs, yeah.
why don't you just go?
Well, I was waiting for you. Yeah, I'll go up if you don't mind.
Yeah, I'm good, huh? Thanks.
Okay.
We have a
Late,
Bravo.
unless you want to just finish it on there.
No, I'll go up there.
Chill, Ernie, chill.
Is that Ernie?
Yeah, it's Ernie.
Morning, Ernie.
Oh, we've embarrassed him now.
Okay. So slightly different. What will the output voltage be if R1 is 1,000 and RF is 10,000? And 0.23 volts is applied at the input.
So you're gonna multiply this time.
Got to multiply and divide.
0.3. What's going into the negative foot?
Yeah, what did you say there, Byron?
I said, Bravo.
You said Bravo?
Delta, because it's going into the negative.
It's a trick question.
Yeah, it's negative. Let's see.
Remember, it's an inverting amplifier.
Oh. Inverting.
So you're putting 0.23 on the negative input.
Well, there's a gain of 10 times 0.23, that's 2.3, but on the inverting input, so the output would be negative 2 point.
Right.
Thank you.
Even old dogs learn something.
That's higher.
Old dogs forget a lot.
So the odds are pretty good. You're going to get one of those,
Trick question.
Yeah, you watch the
one of those gain questions out of this group.
inverting or not inverting input. Yeah.